All right, today we're diving into a theory that, well, it's going to sound a little nuts. The idea that our entire three-dimensional world might just be an illusion, a kind of complex projection from a distant, flatter universe. So, are we living in a hologram? Let's find out.
That's a quote from Leonard Susskind, one of the giants of string theory. And what he's saying is that everything you see and feel, this room, the sky, even you, could just be an image, a hologram projected from some far-off 2D surface. It absolutely sounds like science fiction, I know, but it's a very serious idea that came from a really deep cosmic puzzle.
So yeah, what on earth would make brilliant scientists take an idea like this seriously? Well, it's not just a wild guess. It's actually the result of a decades-long battle to get two pillars of physics to play nice: gravity, the law of the very large, and quantum mechanics, the law of the very small. And the whole story, weirdly enough, starts with black holes.
To really get the holographic principle, we first have to understand the problem it was invented to solve. And this was a problem so profound, it looked like it was about to shatter one of the most fundamental laws of physics.
It's called the black hole information paradox. And here's the deal in a nutshell. Quantum mechanics has a really strict rule. Information can never, ever be destroyed. You can scramble it, you can hide it, you can rearrange it, but you can't just delete it from the universe. But black holes, well, they looked like the universe's ultimate shredding machines.
So let's say you toss a book into a black hole. All the information that made that book unique, the specific arrangement of its atoms, the words on the pages, it all falls past the event horizon and poof, it seems to be gone for good. And eventually, black holes are supposed to evaporate away through something called Hawking radiation. The problem is, that radiation looks totally random. It doesn't seem to contain any of the information from the book. So you've got this huge clash, right? Where did the information go? Well, the clue to solving this lies in a concept you've heard of, but maybe in a different way.
Okay, so the key to cracking this whole thing open is a concept called entropy. Now, most of us learn about entropy as just a measure of disorder or messiness, but physicists started to realize it's something much, much deeper. It's a direct measure of information itself.
Just think about the air molecules in the room you're in. They have super high entropy, right? Because there are just a zillion ways to arrange them that, to us, look exactly the same. Now, imagine trying to write down the exact position and speed of every single one of those molecules. It would take an absolutely colossal amount of information. So you see, high disorder means a high amount of information is needed to describe it.
And here's the crazy part. Two totally different fields stumbled onto the same idea. Back in the 19th century, Ludwig Boltzmann defined entropy as this measure of physical disorder. Then, about a century later, a guy named Claude Shannon, the father of information theory, came up with a formula to measure information in a message, and it was mathematically almost identical. It was the physicist Jacob Bekenstein who really connected the dots, realizing these were two sides of the same coin, and that insight was the key.
So now that physicists had this powerful link between entropy and information, they could ask a brand new question. How much information can a black hole actually store? And trust me, the answer they found changed everything.
I mean, you'd think, right? It just makes sense. If you want to store more stuff, you need more space. A bigger hard drive holds more data. A bigger warehouse holds more boxes. So you'd naturally assume a black hole's information capacity would be tied to its three-dimensional volume. The bigger it is, the more it holds.
Yeah, well, that's not what they found. Not even close. In what was a completely stunning breakthrough, Bekenstein and Stephen Hawking figured out that a black hole's information content isn't related to its 3D volume at all. It's proportional to its 2D surface area, the area of its event horizon. This was just bonkers. It's like being told the number of books a library can hold depends not on the shelves inside, but on the area of its wallpaper. It makes no intuitive sense.
So this is the big aha moment. The solution to the paradox is that the information never gets lost inside the black hole. Instead, it gets smeared out and encoded onto the two-dimensional surface of the event horizon. You can picture it like this. Every tiny little patch of that surface, a size called a Planck area, holds one single bit of information.
And get this, it's not just some vague idea. The math is incredibly precise. The total information a black hole can store is exactly 1/4 of its surface area when you measure that area in these fundamental Planck units. Not a half, not a third, 1/4. It's such a strange and specific rule from the universe, and it was a massive clue that something deeper was going on.
Okay, so this discovery about black holes was already mind-bending enough. They're the densest things we know of. So if the maximum information you can cram into a space is defined by its surface area, not its volume, well, that led some physicists to ask an even crazier, more audacious question. What if that's true for everything? What if it's true for the universe itself?
And that, right there, is the holographic principle. It suggests that our 3D reality, everything we experience, might just be a projection. All the information that describes our universe could actually be written on some distant two-dimensional boundary surface. It's just like a 3D hologram from a credit card, which is really just a pattern on a 2D film.
Now, this idea didn't just pop up overnight. It was built piece by piece over decades. It kicked off in the 70s with Bekenstein and Hawking's bizarre discovery about black holes. Then in '93, Gerard and Hooft took that idea and blew it up, proposing it as a principle for the entire universe. Leonard Susskind then gave it a solid footing in string theory, and then in 1997, Juan Maldacena came along and delivered the most powerful mathematical evidence for it anyone had ever seen.
And the biggest piece of evidence we have for this is something with a crazy name, the ADS/CFT correspondence. But you can just think of it like a perfect dictionary or a Rosetta Stone. On one side, you have a description of a 3D universe that has gravity, kind of like ours. On the other side, you have a description of a flat 2D surface that has no gravity. And what Maldacena discovered is that these two are mathematically identical. They're just two different languages describing the exact same thing.
Okay, so the math is beautiful, it's elegant, but is it real? I mean, if we're really living in a hologram, shouldn't there be some way to see the pixels? To find some physical evidence? And that's the billion-dollar question, isn't it? Is this amazing correspondence just a useful mathematical trick that helps physicists solve tough problems? Or is it a literal description of our reality?
And you better believe scientists are looking. For a while, some were searching for something called holographic noise, a kind of fundamental graininess or fuzziness to spacetime, which would be our universe's pixels. That idea hasn't really panned out. But more promising are efforts using our amazing gravitational wave detectors, like LIGO, to see if they can spot tiny signatures predicted by the theory. And there's a whole new field called celestial holography that's trying to find evidence of this right here in our own cosmos.
You know, in the end, it all comes back to this beautiful question from Jacob Bekenstein, echoing the poet William Blake. He's really asking, is it literally true that our whole world can be described on some distant boundary? Or is this holographic idea just a beautiful metaphor, a bit of poetic license? And right now, we honestly don't know the answer.
Which of course leaves us hanging with the biggest, wildest question of all. If our reality is a hologram, a grand cosmic projection, then you have to ask, who or what is running the projector? And that's a question that takes us right from the cutting edge of physics to the very heart of philosophy. And for now, that remains the ultimate mystery.